At this point in the course, we have two fundamental principles in hand. One, Newton's second law, which we also call the momentum principle, and two, the energy principle, which we also call the first law of thermodynamics. Today we'll add a third fundamental principle, the angular momentum principle. Like the other two principles, the angular momentum principle will link changes within our system to interactions between the system and the surroundings. However, unlike the other principles, the angular momentum principle focuses on the rotational motion of our system. Specifically, this principle relates changes in the rotational motion of our system to the total twist on the system, in the same sort of way that Newton's second law relates changes in the translational motion of our system to the net push or pull on it. We describe the rotational motion of our system with a rotational momentum we call the angular momentum, and we call the net rotational force exerted on our system by agents in the surroundings the net torque. Sometimes we might find it helpful to think about the angular momentum principle as the rotational analog of the momentum principle, which, as we mentioned earlier, focuses on the translational motion of our system. So, for example, you'll recall that earlier we learned how, by observing the translational motion of our system, specifically the change in the momentum over the change in time, we learned something about the net force acting on our system. In the same way, we'll see that by observing the rotational motion of our system, specifically the change in angular momentum over the change in time, we'll be able to learn about the net twist, the net torque applied to our system. However, before we can use this new principle, we need to understand exactly what the physical quantities of angular momentum and torque really mean. This will take us a couple of lectures, so let's get started. First and foremost, we need to recognize that rotation always involves movement about a line that is often called the rotation axis. The physical quantities describing rotation are typically defined with respect to a particular rotation axis. So, when we are dealing with calculating rotational quantities, one of the first things we should ask ourselves is, where's the axis? Frequently, we are free to choose the axis, much like we are free to choose our coordinate system when we're describing translational motion. In some cases, a good choice of axis is pretty obvious. For example, for a bicycle wheel that's held in place and spun, a good choice of axis is the line perpendicular to the plane of the wheel passing through the center of the wheel's axle. However, in other cases, there may be many different ways to choose an axis. Regardless of the rotation situation, making this choice is crucially important. Just as important, really, as making our choice of system. So here's some good advice. Let's try to identify and to choose an axis early on whenever we are calculating rotational quantities. We'll close this lecture by introducing a simple example of a rotating system, which we'll use for the next couple of lectures to introduce rotational quantities. Imagine that we have a particle of mass m that's attached to one end of a rigid rod of negligible mass. The other end of the rod has a fixed location. However, the rod and the particle are free to rotate about this fixed location. Our choice of system here is the particle attached to the rod, and clearly a good choice of axis here would be the line that passes through the fixed end of the rod and is perpendicular to the plane in which the mass and rod rotate. It will be important to specify locations with respect to this axis. For this, we will use the position vector r. So, for example, the location of the particle of mass m with respect to the axis is given by the position vector r sub a m. We're now ready to introduce rotational quantities found in the angular momentum principle. We'll start doing that in our next lecture.